All right, our next intermolecular force is hydrogen bonding. The first thing we need to understand about hydrogen bonding is it's not a bond. So it's called hydrogen bonding, but it's not a bond. It's only about 5 to 10% the strength of a real bond. It's just another intermolecular force. And it's really not that different than dipole-dipole force. It's basically just another dipole-dipole force, except it's much stronger. I'm going to say it's a super strong dipole-dipole. IMF. And hydrogen bonds occur with molecules that have certain types of bonds. And it's molecules with either FH, which is only HF, right? It's the only way you can have an FH bond, OH, or NH bonds. So if your molecule has one of these type of three bonds, and really it's just the latter two, you have hydrogen bonding. Why these three bonds? These are the three most electronegative atoms. And so when you have this kind of XH bond where X is your O, F, or N, you have a very strong dipole here. And this strong dipole makes a strong intermolecular force. And if we think about it, one of our most popular molecules, water, has hydrogen bonding. And so that's kind of why it gets a special name. It's very important in our kind of life. So it's really not that much different than a dipole-dipole force, except it's much stronger. So for example, this would be a hydrogen bond between this OH bond and the neighboring oxygen, right? You have a very strong dipole here. And then this partially negative oxygen is attracted to it. And water is really cool because it can hydrogen bond not just once, but twice, right? It's got two OHs. And so it can actually do this kind of interaction twice. And so that gives water a very high boiling point of 100 degrees Celsius. Relative to its very small size. Water is only about 18 grams per mole, yet it has an extremely high boiling point for that small of size. And it's all due to this hydrogen bonding. Everything about the boiling point versus molar mass, right? Most other compounds will follow a linear trend. For example, CH4, as we increase the period, right? We switch carbon to then silicon, to then germanium, and then tin, right? As we increase the mass, the boiling point increases. And that's the similar for oxygen's group, right? H2S, then H2SE, then H2TE. We can see as we increase the mass, we increase the boiling point. But then if we take a look at where water is, water has a much lower molar mass, so it's going to be somewhere around here, but its boiling point is much higher, right? And that's because we have this capable of hydrogen bonding. Right, so it's kind of the odd one in this series, and it all has to do with its ability to hydrogen bond. Just another example, dimethyl ether, CH3OCH3, has no hydrogen bonding. It does have dipole-dipole forces, though, and it has a boiling point of negative 24 degrees Celsius, whereas something like ethanol, CH3CH2OH, has a boiling point of all the way up to 78 degrees Celsius. That's a massive difference. And really the only difference here between these molecules is the presence of this hydrogen bonding. These two molecules, dimethyl ether and ethanol, are constitutional isomers as well, which means that they have the same atoms. It's just a different type of bonding, right? You have a hydrogen bonding right over here in ethanol. And you can see that the formula gives us the hint that the hydrogen bond is there. And you don't have that in dimethyl ether, right? And you can see how big of a difference it makes in the boiling point. This is also how our DNA sticks together, right? So I'm sure from your biology class, you have kind of two strands of DNA that are locked in one another. The bases form hydrogen bonds, and that's how they stick together. And so if you want to open up these base pairs, you have to break that hydrogen bonding. Of course, you've got enzymes in your body that do so.